stuff going on at the same time.
Okie dokie. This will be an interesting hour.
Well, you couldn't have brought a better wingman on this one, Kimberly.
Yeah, thanks for being here, Paul.
You'll get it. It's fine. It's just flows of stuff.
Yeah.
It's just gravity. I mean,
It's just gravity, man.
All right, we are live.
Everything's gravity.
I think.
Yeah.
Okay.
Okay.
That's a really cool picture, though.
Yeah, these graphics are so good. Man, that's how you make a good infographic right there.
They kind of remind me of those climate graphics. Here, I'll let the audience see what we're talking about here. Those climate, the NASA's been doing those really great, almost artistic looking sea patterns and atmospheric drifting patterns. Here, let me see if I can make this work.
Which one are you looking
I'm
at?
looking at the one with the shapely attractor and the dipole repeller and the local group motion and all these cool arrows going around.
Yeah.
Is that the one?
Yes.
Yeah. That's really cool. Yay. Okay, I'm going to say hi to a bunch of people, and then we'll probably need to get started. Hello to Adam Synergy, Alex Economou, Bill K, Citizen Gold, Daniel McCool, Giselle Sabarin, Guido Bibra, Tour, James Haney, Jessica Feltz, John Seffel, Johnny Zed, Kimberly Cartier, Lars Rye, Jepson, Lillian Brennan, Malcolm Bond, Nancy Graziano, Ott Kappelma, Paul Gracie, Rick Schwartz, Ronald McCoy, Sylvan Westby, Susan Murph, T. Chris Wheeler, Tak Tang, Thomas Traniker, and Timothy Barnes. Welcome to the Weekly Space Hangout. It's February 3rd. All right. It's 12:06. I don't think I have anything else to do. Why don't we just get started?
Let's roll.
Let's
do this.
Let's be done. Okay. That's me. All right, here we go. Hello, everyone, and welcome to the Weekly Space Hangout for Friday, February 3rd, 2017. I'm Fraser Cain, publisher of Universe Today. This week, we're going to be talking about cosmic supervoids, oxygen on the moon, and first science from Keck's vortex coronagraph. That sounds so cool. And
Such a cool name.
just maybe, we'll get some information on the holographic universe, but it's going to take a little bit of prodding.
If you're nice.
From a hostile, correspondent.
I am not hostile.
Reluctant.
I am a curmudgeon. I will accept curmudgeon.
Correspondent. So, joining us this week, we've got don't want to jinx it, Dr. Kimberly Cartier.
Not doctor yet. You're going to jinx it, Fraser.
What?
Hello, everybody. Happy Friday.
That's all in the... Oh, there we go. Hold on. There we go. All right. There she is. Yay.
Hello.
And then we've got Dr. I can't jinx it now, Paul Metzutter.
Already done. They can't take it away.
Oh.
That's right. It's mine forever.
Very comforting.
And
Yes.
We've got a very special guest this week, another doctor, Meredith Rawls. Meredith, welcome to the
Hello.
Weekly Space Hangout.
Thank you.
And you're all going to understand in a second why I am super, super excited that we've got Dr. Rawls here on the Weekly Space Hangout. People are saying that my sound is low. Really? My sound is low or their sound is low? Please let me know. Because it looks like the audio is pretty... it does look a little low, doesn't it? Okay, here, let's crank it up a bit. There we go. Okay, great. So, sorry about that. So, once again, this is a live broadcast. If you're watching this live, you can go ahead and ask us any questions about our topics. Just go ahead and type it in. If you're watching it on the YouTube chat, you can post it there. If you're watching it and use the Slack chat, that's the one that's down here. And, of course, people will post the questions that get asked over in the YouTube chat and put it up in the Slack chat. I'm pointing in the directions that I see on my screen, which is not the same as the directions that you see on your screen. It's weird that my audio level is low. I've cranked it up, but we'll see how that works. Okay, well, let's get on with our very special guest, Meredith Rawls, welcome to the Weekly Space Hangout. Who are you and what do you do?
Isn't that an excellent question? Well, my name's Meredith Rawls, and I am a postdoc here at the University of Washington. I work with the Large Synoptic Survey Telescope data management team, which is a lot of words, but I can explain what they mean. And I finished my PhD last year at New Mexico State University studying stars.
Right. Well, the part that got my attention was the fact that you're working with the LSST. And I believe I've gone on record many times that the LSST is like the most exciting observatory upcoming observatory to me. And I think part of that comes from the fact, I've been reporting on space and astronomy for 17 years now, and there's so much work gets done using these gigantic databases of observations, Sloan Digital Sky Survey, things like that. LSST, can you explain what the LSST and how it's going to sort of take all this to a ridiculous next level?
Sure. So it's under construction right now on a mountain in Chile, and basically what it's going to be like an 8.5 meter main mirror. And the camera that's being built is the largest camera ever built, which is kind of awesome. It's going to be the size of a small car, just the camera. And it's going to take a 10-year high-resolution movie of the entire southern sky, beginning in 2022. 6 different color filters. And the idea is that we can really map the changing universe much better than we've been able to in the past, because we'll have the full sky coverage, we'll have an entire 10-year movie basically that we can delve into, and we'll have real-time alerts for things that have changed so people can follow up on the things that they care most about.
I'm just putting up a picture of the telescope, and there's like a person to scale. I think people can sort of see this little person here and this gigantic telescope. So let's talk just about scale of the telescope itself, and just kind of compare it just in terms of size to the other observatories that are out there. You say it's not going to be the biggest telescope.
No. Yeah, so Keck, for example, is bigger. Keck is like a 10-meter mirror, and LSST is only 8.5 meters. So it's not like the biggest thing you've ever seen, but it's still a really big telescope. Right. And the way it's being designed is so that it can slew around the sky and point in different directions relatively easily. So it's kind of a short, squat design compared to what you may have seen for other telescope schematics.
It's fast.
So a lot of really cool engineering challenges to make it all work together.
Yeah, it's super fast. In sort of observational astronomy terms, right?
Yeah. It actually, every time it takes an image, it's a 3.2 gigapixel camera for one, which is like hundreds of iPhones every time they take a picture. And it only takes 2 seconds to read that out fully, which if you've ever done observational astronomy, that's just ridiculous. Normally you're sitting there for like a minute waiting for all the counts to get off your CCD and onto your computer. But it's super
and so And it is also, as you say, fast in terms of just like how quickly you can take that image, and then it can slew to another position. So how much of the sky is this going to be surveying on a regular basis? How fast is it going to be going through the sky?
Right. Basically every 3 nights, assuming the weather cooperates, we're going to have an entire new full sky coverage map. Now there's a little bit of variation there because there are also some areas of the sky that we're focusing on more. There's these deep drilling fields and certain areas where we want to get, hammer it a little more. But the overall idea of the telescope is to get the full southern sky. So this is not a telescope, for example, where you could propose, hey, I want to look at my favorite object next week.
Check the
please.
Database. See if it's in there.
Yeah, right. Yeah, it's probably in there, but maybe not with the exact cadence that you were hoping for.
So then, how in there is this stuff going to be? How would you compare the images that this thing, it's going to be returning the entire sky that it can see every 3 days? How does each one of those images compare to what's out there already?
So it's going to go really faint for one. So there's a couple different ways to think about it. We're producing like this real-time alert stream, and that is what my team at University of Washington is thinking about. So I'm mostly preoccupied with okay, we need to compare each new image with each old image and find things that changed and be not super wrong about it and move on with our lives. But there's people who really, really are excited about the fact that it can see really faint objects. It's going to go down to about 26 the magnitude, which is quite faint for seeing, distant galaxies in all 6 different color bands, and maybe 24th magnitude in some of the bands, but in there. And so every year or so, there's going to be a data release that is the super faint, all co-added together images, so you can see those fainter objects. So there's a couple different approaches for the data.
Right. I mean, when I think about things like the Hubble Space Telescope, I mean, you can take but things like the deep field, the ultra deep field, things like that, where Hubble stares at one specific portion of the sky for a long, long time and produces incredibly faint images. But at the same time, but for most telescopes, if you want to see something, I mean, this is sort of the whole problem with Planet 9 right now, is that Mike Brown and crew know it's out there, but they don't know where it is, because space is big, and to take a high enough resolution image of any one portion of the sky, you need a telescope that can go to a very faint level, and you need to have it stare, and you just don't have the time to survey the entire sky.
Right. Well, one nice thing about LSST is that the field of view on the sky is significantly larger than the full moon. It's like a 3-degree field of view for every picture. So you're getting that coverage a lot faster than you would with something like Hubble that only covers a tiny little chunk of sky at a time.
Yeah, and I think the reason why I'm so excited about LST is it's just one of these Swiss Army knife tools that can be used. I mean, I talked to many astronomers, and each one of them is like, if they're in supernova, if they're looking for planets, if they're looking for asteroids, if they're looking for anything, they have an interest in what's going to be coming out of this observatory.
Yeah, absolutely. And that's what we're really excited about, is that if you care about any area of astrophysics, LSST is probably going to do cool stuff for you. It's not just a dark energy telescope or just an asteroid finding telescope. It's doing all this stuff.
Speaking of data, how much data is going to be pouring out of this observatory?
A ridiculous amount. It's going to be on the order of 15 terabytes every night. So that's, a lot more than your computer can hold. And it's a little terrifying. So over the course of the 10 years, we're talking petabytes of data. And that's before you consider the catalogs that we're making, which will also take up space.
Well, I guess that's my other question. I mean, you're going to be taking these raw images of the sky, but then you're going to be processing them in such a way that you can start to, people can search for stars and see how they're changing over time, things like that.
Yeah, so all of the software is going to be run on a big old server in Illinois at the NCSA facility. So there's like 2 dedicated cables that are taking the data straight from LSST in Chile to Illinois. And that is where all of the software pipelines that we're writing will operate. But the cool thing about our software is that it is completely open and public, and that people can see how we're writing it, contribute to it if they want. Once the data is actually there, we'll have a way for them to actually tweak it and add their own pieces to it, and then run it on the data on the server, because we don't want people downloading this data themselves, because that's not feasible or realistic.
Right. So they'll be running Hadoop queries on your database.
Yeah, it's a whole different way of thinking about how to process data in astronomy, because I'm used to the model of you go and you sit at your telescope and you download your thing and you get your USB stick and you make sure nobody, touches it, and then you go and open up all your favorite images on your computer. But that's not how this is going to be.
And I mean, I think of some recent observations and recent controversies, like Tabby star, for example, the alien megastructure star. This is the kind of thing, I think, that you could go, well, how has this star looked over the last, since the LSST has been operational? Right. I don't know. Let's go and look how that star looked every 3 days for the last 15 years, or whatever is the amount of time, right? I mean, these kinds of, you can now look back in time through the data that you have to answer some questions.
Yeah, absolutely. And that's what we really want to enable, because we're going to send out these alerts that we're calling them. It's basically this little packet of metadata about something that changed in the sky. And it will have a little postage stamp included with it, and that an actual, picture of that chunk of the sky with the object in the middle. And it will actually also include the entire history of that object also. So now it's not going to have a cadence like Kepler, right? It's not going to be every 30 minutes there's a data point. But, if we've observed it every week or so on average over the course of the 10-year survey, that information will be available in the alert. So you could totally do something like that.
Does that sound intriguing, Kimberly? I know I use the M. Apparently, I use the M word. I use the.
You used the
I
M
know.
word.
Hey,
It wasn't me.
I'm free
It wasn't
to
What?
speculate on alien civilizations. I am not the astronomer.
You are completely free.
Oh,
to-
is megastructure the M word
yeah,
we're not supposed to
megastructure
say?
the M
Oh,
word,
okay.
So can you give us an idea then of the kinds of discoveries that we should be turning up, the fields of research that are best going to benefit from this instrument?
Sure. So there's a couple that stick out to me. If you talk to somebody else, they'll probably have their own two favorites. But one I've heard a lot about is asteroid detection. So as you probably know, there's lots of asteroids in the solar system. And I'm not a solar system scientist, so this is kind of a new thing to me. But we're going to find, like it or not, lots of stuff moving across our images. And we can calculate orbits from that because we're going to have this long time series, and we're going to find a whole bunch of new asteroids, and we'll be able to get a feeling of their composition because we'll have 6 different color bands. And we'll also be able to get, are they going to come near Earth, which is a question lots of people really should care about. So it's going to be an excellent asteroid hunter. And the other area that I think is really cool is supernova science, because again, we're going to be monitoring the sky so often, we're going to find tons of distant fate supernovae doing all kinds of stuff. And that's cool. Everything from like what's actually physically happening in a supernova, which is a little more up my alley, and the whole universe expansion business that of course we would like to nail down. So
yeah, I mean, stuff here in the solar system. I've got a question here that just came up from Malcolm Bond, which is, will there be any public time on the LSST? And I think that's the whole point, is that it's just an open database on the internet, right? There's no.
Yes, so there's no like explicit public observing time, so to speak. Like you can't say, hey, please look at my favorite target. But the alert stream, I believe the idea is for that to be completely public. Although because of just the volume, you might need to like log in some fashion. I think we're still building that infrastructure, so I can't tell exactly how it's going to work. But all of our software is 100% public. It's all like you could log on to GitHub right now and see the mistakes I made last month if you want. Like it's all there. And the data releases, the annual data releases that have the catalogs and all that, they are publicly available to US and our partner affiliate countries, which is a long list, but not technically everywhere. So, but if you are a collaborator with somebody at one of the international institutions that's collaborating on LSST, you'll have access to those data release catalogs immediately. And if not, you'll have to wait some period of time. So it will eventually be 100% public, but there is a small waiting period for the data release, annual data
Right.
releases.
And so if you're a skilled database hacker and a citizen scientist astronomer, you can go in, run queries, discover asteroids, name them after your friends, find comets. That, I mean, I think that for a lot of people, this is just going to be a wonderland. One of the things with the Sloan Digital Skies Survey I know is that there's not only the sort of the observational data and some of the designations of the stars, but actually follow-up observations of like spectrographic information, like actual chemical constituents of those stars. Are there plans to sort of follow up with some of that information as well?
Yes, I don't have details about specific plans off the top of my head, but I know that it is a top priority. That there was a white paper that came out, I want to say last year, where a bunch of people kind of got together and were like, okay, LSST is going to be great, but it doesn't have a spectrograph, like you say, so we're not going to be able to learn everything. So, what optical infrared spectrograph capabilities would really work well with LSST, and how can we get that up and running? So we have a few years to get that sorted out still. I think they've identified some potential places, and it may already even be in the works. I haven't been up to date on that. But I mean, I've done a lot of work with spectra in the past with binary stars and chemical compositions and stuff. So I'm really excited to see what kind of simultaneous or even follow-up observations that we can get going systematically with spectra.
Yeah, binary. You forgot about binary stars. You can discover those.
Oh yeah, no, we'll find tons of those. Just general
Gravitational
people aren't as
microlensing
excited about
events.
binary stars as I am. Oh yeah, absolutely.
It just goes on.
We're gonna find weird variable sources we didn't even know to look
Right.
for. Like that's what we always find when we have these new missions. It's like, what the heck is that
And
thing?
that's the thing,
So,
right? Is that,
it's gonna be great.
for example, we can find a star that clearly has an alien civilization surrounding it, some kind of megastructure, and
Always
right,
a megastructure.
and then you can then go back and look for other stars that have a very similar
Sure.
behavior,
Color,
and then
whatever.
then try to use that to sort of figure out what's actually going on, that it might be something other than aliens. Yeah, again, I'm really enthusiastic about the potential of this. Why only the southern hemisphere? Why don't we get one in the north?
Well, you want to pay for it? We'll build one.
Canada will gladly pay for a north-based one. We've got the Gemini. We contributed to that, so we're on board. I speak for all Canadians.
The southern hemisphere, as you know, the southern hemisphere, you can also see more of the galactic plane. So, and Chile is an excellent observing site in terms of being high and dry and good weather. So those are kind of
To give us some time frames then. When should we see first light from the observatory?
2019, we will have a commissioning run. So the way that's going to work is they're going to have the camera itself is like a whole bunch of CCD cameras kind of in a grid. And they're called rafts. They're little not 3x3 things. And all together you have the 3.2 gigapixel camera. But that's a lot of pixels and camera parts to work together. So in 2019, they're going to have a commissioning camera that goes on sky. It's just a single one of those 3x3 grids. So it's a smaller field of view, obviously. But we will start doing like a mini test survey in late 2019 with that. And that'll be great because we can test our software on the actual images from the actual telescope that uses the actual filters and all of the things that we think we're thinking about. But I'm sure there's something that we'll miss and need to adjust. So that is the initial. We'll start getting some data, but then the real survey starts properly in 2022 and goes for a decade.
Wow. And if it is as successful as I think it will be, then there will be one built for the north, I think.
I hope so. That'd be great.
The whole sky. It feels to me like, as a fan, not an actual working astronomer, that this feels like more of the future. That now that we have the ability to gather data at this level, that it's about supporting searches for stuff that you think of after the fact, that you could then go back and have this historical record of the sky. And I think it really seems that the changes that are happening in the sky is more vibrant and more chaotic, and things are happening more often than I think we ever thought, and that there's a lot of science to be gained. So
yeah, absolutely.
Yeah, I'm absolutely the biggest fan of this observatory.
Good, me too.
No, absolutely. So you don't. I'm free to be biased towards it. So I was going to wonder. Just want to throw a quick question off to the other panelists, Paul and Kimberly. Either of you guys have anything that you're going to be looking for in the LSST data? Kimberly.
You can go, Kimberly.
Okay, go, Paul.
Okay. So I'm very interested in mapping the large scale structure of the universe. And right now, when we do mapping and we want very precise mapping, especially to measure things like cosmic voids, which Kimberly is going to tell us more about, we need very, very precise measurements of redshift so we can get the very accurate distance measures. So we're limited to using spectroscopic surveys. Now, LSST is primarily a photometric mission. So we get, it's a little bit fuzzier. You don't get as precise measurements, but you get a lot of them. And we're actually looking to develop some interesting techniques where you can still squeeze out some interesting and very high precision measurements of things like the shapes of structures and the flows of matter at very large scales using noisier data, but tons of noisy data.
Totally.
Kimberly.
I think both you, Fraser, and Meredith have sort of said the things that I'm really interested in is stars doing weird things.
Yes.
Different variable stars that we've never seen before. We've only seen a handful of that particular type. Obviously, Boyajian star is a big mystery, and we just don't know if there are others like it. But if we get enough data and enough time domain data of more of these F stars, or just any kind of star doing something really funny, we may luck into something else that'll help us explain a lot of these weird mysteries. So that's sort of what I'd like to see.
Very cool.
No surprise there.
So Meredith, where can people find out more and sort of track the progress on the mission?
Sure. So our main website is just, I think it's lsst.org. Let me make sure I'm not lying to you.
Yes, it is.
Yes, it is. And there's also, from there's a whole bunch of links to other great resources that are related to LSST. It kind of depends on what level you want to dive into. One new resource that I really like is community.lsst.org, which is a great forum that's been put together. It's a little bit, some of the conversations are a little technical. You can see some of the questions that we're discussing in the data management team, like, really nitty-gritty programming stuff. But there's also some bigger questions about, hey, what's going on in the project lately? What's some of the news? And anybody can make an account there and join the conversation. So if you have a really strong opinion about, like, I don't know, whatever weird technical thing we're discussing this week, you are welcome to chime in. Or if you have a question, if you're trying to use our software and you're having a problem installing it, you can totally post maybe I'm doing something stupid, but this is giving me a weird error, and a real person will actually help you.
And for people who are more technically minded, they can start to develop the software that they're going to be using to, some of the queries they're going to be looking for. Can they get a sense? Have you got your documentation starting to come together?
Yep, we are definitely working on documentation. We're playing a bit of catch up right now, but we have a great team of folks based in Tucson that are working on making sure that as we get new pieces of code, we are also explaining what they do. And actually, pretty soon here, I think in the next couple of months, we're going to have a website that is it exists. It's pipelines.lsst.io, and it exists, but it's not super easy to find things on at the moment. So that's being overhauled in a way that if someone wants to use our software and they land on that website, there will be like tutorials and, what the heck is this weird software package do for you, and stuff like that. Because we're testing our software right now on data from other telescopes, obviously, because we don't have LSST data yet. So if you want to do photometry on data from another telescope, it's quite possible that our tools will be helpful for you.
Fantastic. Well, thank you so much for joining us, and we're going to move on.
Well, thank you for inviting
No problem.
me.
And when you actually get some first light, hopefully you'll be able to come back and tell us how that's going. So we're going to move on to the other stories. You figured you might stick around. We'll kick some of this your way if it's appropriate for LSST. But let's move on to the rest of the stories that we've got this week. All right, so first I want to talk about let's talk about first science from Keck's vortex coronagraph. Kimberly.
Yes, so I remember talking last week a bit about coronagraphs and all the wonders that they can do. And this was a coronagraph I had no idea was even being developed, but it looks like it's going to do great things. It is called the vortex coronagraph, which is just a fantastic name for a coronagraph. And it's been installed on Keck's near-infrared camera 2, which is the main infrared camera on the Keck telescope. And it was designed a few years ago specifically to image closer to to image a planetary system closer to a star than traditional coronagraphs were capable of doing, which in and of itself is a great thing. What's cool about this coronagraph is it's designed, when you look at it, it sort of looks like a miniature CD. It's designed with concentric grooves that have gouged out of a synthetic diamond disc. And when light hits this coronagraph, instead of just blocking out or masking out the starlight in the middle, it actually deflects the light into an interference pattern that then cancels out the light instead of just blocking out the starlight itself. It creates the negative interference pattern, which lets you look closer to the center of that system than traditional coronagraphs are capable of doing. And the first two scientific discoveries have come out of the vortex coronagraph, one of which is the discovery of a brown dwarf orbiting only at 23 astronomical units from the center of the star, from the center of the system, which is about the orbit of Neptune. And this, the distance is about a 2 to 3 times improvement of the best coronagraph discovery that we've seen before. So we're getting closer and closer to the inner parts of the solar system, sort of where the frost lines of solar systems are, which is sort of the dividing line between where planets become either rocky or gaseous, where things like water ice, methane ice, and carbon monoxide ices are capable of forming. And we've also imaged a protoplanetary disk, getting pretty close to the center of that star, since the star is only a few hundred light years away. And combining that with infrared Spitzer and WISE data, they were able to discover that the disk is actually mostly made of olivine, at about pebble-sized olivine grains, which is one of the primary silica that forms Earth's mantle. Which is pretty nifty.
Huh. So, and isn't olivine produced in the presence of water?
I believe so, yes.
Interesting.
Water itself is not a super huge discovery because water is pretty ubiquitous. It's easy to form and it's pretty much everywhere. But what I find really, really interesting about this is the fact that we're starting to push more and more towards the centers of these star systems. We're getting closer to the types of orbits where Earth-like planets can exist around Sun-like stars. So we're still searching for that holy grail, and we're pushing more and more inwards.
And so once again, I mean, this, you know, when I look at this, these images, we're seeing them face on, which is again a sort of a kind of detail that we would never see before. It was all radiometric data. We knew the speed that the star was being yanked back and forth, or we could see the transits as the planet was going in front, and then try to get at the atmospheric data from that. But now we're seeing these face-on solar systems. Of course, last week's mind-bending 4 planets in one image,
the best movie of 2017.
That is all thanks to the coronagraph. And so the key then,
yeah, exactly. Direct imaging finds planets, that transits, that radio velocities, that astrometry, that microlensing just can't see, because they're looking at different planetary system alignments. And one of the key drawbacks with direct imaging has always been that the planets need to be very far out, very far away from their stars, so you can see the very faint light coming from the planet itself. The planets have to be very young, and when you're so far away from the star, you cool very, very quickly. And so you're limited as to not just how close to the star you can image, but the ages of the planets and stars that you can actually look at. But with this type of coronagraph, if you can go closer to the inner parts of the solar systems, you're not limited by either the distance or the age, or you're less limited by the distance and the age that you can see. So we'll find even more of these types of planets.
And so the image that the state of the art right now with this coronagraph is to bring you in, as you said, to the ice line. So that'll let us see giant planets, Jupiters, Saturns, things that are orbiting out there.
Yeah, exactly where they are forming, and the types of planets that may, in some instances, actually migrate inwards to be these hot Jupiters or hot Neptunes that we've been seeing.
So, you know, and I guess the goal here is that you're going to be able to look at and survey many, many, many places out there and try to see, as you say, them forming. You're going to see Saturns and Jupiters around other stars as they're in various stages of formation, from the 4.5 billion years after that we have now to the stuff that's just hundreds of millions of years or old.
Yeah, and exactly. These two scientific discoveries sort of bookend the types of discoveries that we'd like to see, from the initial protoplanetary disks with the pebble-sized grains and maybe a few planetary gaps, all the way down to the already formed planets, or in this case, the brown dwarf that they discovered, that will eventually undergo some sort of dynamical process and maybe move around a bit.
Very cool. It's not enough, though, I guess, is the problem.
It'll never be enough, at least for me. I want to find all the planets, all of them everywhere. imaged in every type of way you could possibly do. I want to see their surfaces. I mean, I have a wish list that's a mile long with these planets, but
Yeah.
what can I say?
Awesome.
I'm an idealist.
All right, Dr. Paul Matsetter, let's move on. You're going to be talking about oxygen on the moon.
Yeah, unless you want me to just skip to the holographic
if we have
principle.
time in the end, we'll get to the are we living
All
in a
right,
hologram?
fair enough. Now I'm all excited about it. Now you're going to take it away from me.
Don't worry. Don't worry. Lots of time.
All right. Yeah, so some researchers studying data from the Japanese lunar orbiter Kaguya that was a mission almost 10 years ago. It orbited the moon, I think, for a year and a half. And they're looking back through the data, still mining that data to pull out useful stuff. And they found that oxygen ions are streaming out of our atmosphere along with the solar wind. And when the moon is behind the Earth, those oxygen ions can make their way onto the surface of the moon itself and actually get embedded a little bit in the lunar regolith. About believe the phrase from the paper was tens of nanometers deep into the lunar soil. But that's interesting because oxygen gets in our atmosphere from life itself. The Earth, when it initially formed, did not have this much oxygen in its atmosphere. It's created by photosynthesis. And we don't have a very good picture of the history of oxygen in our atmosphere, but it turns out there might actually be a record of it sitting on the surface of the moon.
So we have to go back.
We got to go back. We got to check it out. We got to, or I suppose we could remotely study it too. But no, we totally have to go back.
But I mean, we have a record of oxygen levels here on Earth. You know, crack open an old rock and smell the atmosphere that comes out, and that gives you an idea of what, and that's how scientists know what our atmospheric levels were in the past. But this tells us, so right. What does this tell us that's maybe different from what we can find by cutting rocks in half?
I think those cutting rocks in half kind of give you little snapshots of little points of time and very, very rough snapshots of points in time. This is the process of billions of years of oxygen ions making their way out of our atmosphere onto the surface of the moon, getting imprinted where it hasn't been disturbed hardly at all. You know, there's no erosion, there's no geologic processes. There are some cosmic rays, there are some solar wind that carry oxygen from the sun itself. So it's not 100% pristine, 100% pure, but it gives a relatively untouched record, potentially, of the total history of oxygen in the Earth's atmosphere.
So, I mean, it would almost be like doing core samples, right? You could like go to the moon, because we have to go back, take your, have your oil drillers who are now on the moon, Bruce Willis style.
I saw that movie.
And they are running some kind of core sample where they're just drilling down and they're bringing out oxygen levels.
Where the core sample goes 20 millimeters or 20 nanometers down.
You need the best in the world to...
Exactly. That's a very, very tough operation there.
Yeah, that's really cool. That's really good. Okay, we're going to move back to...
I just think it's cool that life, oxygen created by life, is ending up on another celestial object.
I wonder if that same process could be used. Now we got to go to Mars, actually. So if we go to Mars and we dig into the surface of the Martian moons, Phobos, Deimos, would you see the same thing? Would you see the history of the Martian atmosphere in the regolith of those Martian moons as well? Also a portal to hell, but
perhaps.
Yeah, that would be cool. One person got my Doom reference there. All right, let's move on. Kimberly, you're going to be talking about. You're going to show up, Paul Matsetter. You're going to be talking about supervoids.
Oh, I highly doubt I'll be able to show up, Paul Metzetter.
I have full faith
I'll be
in
phoning a friend
You can
at
call a friend at
various
the right
points.
time. All right.
I'm sure. Phone a friend. You may phone a friend this time. So new simulations of the local supergalactic universe have started to probe the shape and size of a local supervoid, which has been termed the dipole repeller, which is a terrible misnomer in many ways as to what's actually happening. But it is a local underdensity of material, dark matter, and such, sort of at the opposite end of our local galactic universe from the Great Attractor, that is making us move towards the Great Attractor at a greater speed than we previously thought, and has been shaping the local supergalactic universe. And so what they've done is they've taken measurements of the positions and motions of hundreds and thousands of galaxies from the Cosmic Flows 2 database, and they've mapped the gravitational structure of the local universe and been able to track the motions of these galaxies forward and backward in time to locate the center of this gravitational underdensity of material. And when they track the galaxies backwards and forwards, what actually happens is something that very much looks like an electric dipole shape is created by the motions of these galaxies. It's not an actual dipole because gravity does not act as a dipole, it only repels things. But the fact that there is such an underdensity of material at the exact opposite side from a great overdensity of material like the Great Attractor and the Shapley Attractor makes the gravitational flows of these galaxies appear to have some sort of dipole moment. So I feel like the fact it's called the dipole repeller or named the dipole repeller is a terrible misnomer, though the flows sort of look like a dipole moment. It is definitely not a gravitational dipole. So Paul was discussing with me before, like the global implications of what this is, and things like the Great Attractor and the Shapley Attractor have been known for a while, and it's been greatly thought that they are the dominant forces that are shaping the local supergalactic universe outside of the local group and things like the Coma Cluster and the Hercules Cluster and such. But it may turn out that not only are the attractors the dominating forces, but also this underdensity, the dipole repeller, as a dominant force shaping the local supergalactic universe.
So when you use that,
which may mean that we're measuring the attractors
when
wrong.
you use that term repeller, I mean, that makes, repeller, and you're using air quotes, which is handy, but, I think it makes a person think about some kind of anti-gravity, some pushing effect.
It definitely is not an anti-gravity. It's almost acting sort of how the moon acts to create the tides on Earth, in that the moon is never pushing away on the opposite side of the Earth. It's just a gravitational gradient that goes from a lower gravity to a higher gravity that makes it appear like there is some sort of flow in a single direction.
Right.
So it's not really
actually
a very steep gravity gradient. Yes.
Actually, hate to burst your void bubble. It is literally repelling.
Really?
Because I'm sorry. Because voids are empty of matter, but they're full of dark energy. So just like a universe dominated by dark energy has accelerated expansion, its expansion is accelerating. If you take a pocket of the universe, get rid of all the matter, is now dominated by dark energy, it will literally expand relative to its surroundings.
But is it more... There's not more dark energy in a supervoid than there is in something else. Isn't dark energy a sort of a constant pressure for every cubit of space?
It is a constant pressure. Yeah. You're right. You're absolutely right. It is. Dark energy is constant. But if I fill up a space with matter, then the gravitational attraction of that matter can counteract the repelling nature of dark energy. If I get rid of all the matter and I only have the repelling nature of dark energy, then that local patch of the universe will expand relative to the average. So it will literally look like an expanding soap bubble and actually push on
But
stuff.
if I understand like what's going on here, you've got the great attractor, which is an overdensity of mass on the one side of the galaxy, and then you've got a place that has less density. And so instead of us being kind of torn in two, pulled equally between two opposing directions, you've just got one that's just lost all hope. And it's letting the other one pull us towards it more strongly than even if it was like the normal density of space, right? It's less dense than the normal density of space at the largest structures. And so...
Right. So on one side, we're being pulled to the great attractor and the shapely attractor. And on the other side, we are being pushed away from the dipole repeller.
All right. Now, I mean, I do understand that this is your specialty, and you've got a whole,
See, this is why I have a phone a friend.
This is why you phoned a friend. All right. Well,
it is super weird to think about. It is super weird to think about of space actually pushing. It is only because we live in a universe that includes dark energy. If there was no dark energy, we would not be having this discussion.
I think I was thrown off by their discussion of subtracting off all of the expansion of the universe due to dark energy and trying to factor that into how that changes the gravitational gradient across this whole superstructure.
Yep. Yeah. So of course, we do take away the global dark energy effects of the general expansion of everything to look at these more local motions. But those voids are full of dark energy. 100%.
Or that's all that's
There's
left.
No dark energy with planet studies. There's a reason.
There's nothing left, right? They've just got dark energy. They don't have the dark matter. They don't have the stars. They don't have the galaxies. They just have dark energy going for them.
I guess another way. No, I don't want to say that.
You know what?
No.
We've got enough time now for us to have another conversation here, Dr. Paul Metz-Sutter.
Yeah.
And this is
all right.
Is it true that we live in a hologram?
Well, I mean, what do you mean by hologram, Fraser?
So I'll give you a little more setup here. So this week, I guess, zipping around the newsospacosphere, which is the term I think it's called, there was more evidence that we live in a hologram, that our universe is a hologram and not... Then it all fell apart because a lot of these people have no idea sort of how to report on cosmology and science and physics. A few other people took a more nuanced, skeptical view. Over here at Universe Today, we just went, we're not touching that. Paul's going to just yell at us. So
I'll touch it.
Yeah. So until, but I actually am planning to do a video on this. So I thought I would sort of drill you now, get some information out of you, and then try to incorporate that into the video that I'm about to talk about. So Paul, Matt, sort of,
fair enough.
What is the holographic principle?
Okay, maybe, and that's a big giant maybe. We live in a universe with 3 spatial dimensions and 4 forces. With me so far?
Yep. Gravity.
Okay.
Strong
nuclear, weak nuclear, electromagnet. Yep. And we understand 3 of those forces in terms of quantum physics and quantum field theory.
And how they were...
electromagnetic, weak nuclear.
And how at the early universe they were all aspects of each other.
Exactly. So, but we don't fully understand gravity. And in particular, we do not have a quantum picture of gravity. That is an open question. Lots of possibilities. We're still playing around. Lots of deep mathematics. One understanding of quantum gravity, of what quantum gravity might be, is that maybe, and this is something that just kind of appears in the math, that we don't actually live in a 3-dimensional universe with gravity, but instead we live in a 2-dimensional universe with no gravity And at low energies, wave your hands, it looks like we live in a universe with 3 dimensions and gravity. And I'm not going to take you from point A to point B in that discussion, because it's just like a whole bunch of math.
But right.
And that is the holographic principle.
I'm gonna need you to do the math. No, but I guess the point here is that this is one way to help explain the early universe, isn't it? One of the ways to help us understand how we got from a singularity to the universe that we see today. And
right, because we know the singularity isn't really a singularity. It's just a point where we recognize our understanding of the forces of nature break down. So if we can understand quantum gravity, we can possibly understand earlier and earlier epochs in our universe, down to the first microsecond, the first femtosecond, the first picosecond, et cetera, et cetera. So if we get a picture of quantum gravity, we can better understand the very early universe. So maybe in the very early universe, in the first microsecond, the universe really was a 2-dimensional thing and there was no force of gravity. And then later on, as it cooled off, as it expanded, things happened, and our 3-dimensional universe with gravity kind of emerged. That is the holographic principle at work. And so now the question is, okay, I have a rough sketch of what a quantum picture of gravity might look like under this holographic principle. Do we have any observational evidence for or against these models? Can we even pick it out of the data? And the best place to look is the cosmic microwave background, which was generated about 300,000 years into the Big Bang, so well away from the first microsecond, but it's the closest we can get right now. And some researchers studied the cosmic microwave background and took some very, I don't want to say sketchy models, but like put the barest hints of what this kind of picture of a holographic universe might look like, made some predictions and looked at the data, and they were able to manipulate their models enough that holographic cosmology is compatible with our data, with the level of uncertainty in our measurements. We can't exclude the models with our current observations.
And your job as a physicist,
and that's it,
is to look for the things that destroy your model, right? You're looking for, something that shows that you're wrong. Because as soon as you do, then that throws your theory in the garbage.
This is scientific method 101. This is, I form a hypothesis and I want to test it. And in cosmology, we form hypotheses and then we look for observations to be able to confirm or refute those hypotheses.
And all that happened this week is some physicists found that the theory was not invalidated by observations so far. But that still doesn't mean that it's true.
And they had to torture their models because we don't fully understand the models yet. The mathematics pretty wonky. So they had to exclude some regions of the data. Not all classes of models are permissible, et cetera, et cetera, et cetera. It's a step. It's a step.
Right. And I mean, I always like this to the search for dark matter, in that we still don't know what dark matter is, but we're getting better and better at figuring out what it isn't. And so
yes, exactly.
If you can't figure out what it is, then the second best thing you can do is just try to figure out what it's not until you've run out of things that it's not.
Yeah, exactly. And if the data are never able to tell us about what quantum gravity might be, if the cosmic microwave background can never distinguish any of these models from vanilla, inflation, lambda CDM, concordance cosmology, then we need to look somewhere else.
And I mean, of the holographic theory is trying to do the same thing that inflation is trying to do, trying to help understand how we got from the singularity to the laws of the universe as we understand them today.
Yeah, exactly.
And to match the observations that we see.
Yep.
And those are the big ones. I mean, inflation is the big one, right? But
yeah, I mean, inflation is wildly successful with the small caveat that we don't really understand it at all. But it's able to explain the data really well. And I wouldn't say there's two big ones. I'd say there's inflation and then a bunch of little ones that might be intriguing ideas, but we just don't have enough observational hooks.
Very cool. Well, I think we still don't understand it. No, that's fine.
No.
Man, I feel like this whole discussion really highlights why I'm not a theorist.
That's like pretty much where I am. I'm like, whoa.
Just There's I don't know though, right? What?
Also, why I don't do dark matter or dark energy stuff. I like things that I can see.
But you're going through the exact same thing, Kimberly, with Voyager Star, which is that you're trying to figure out what it's not.
But I can still see it.
Sure.
I can still measure what it's
see
not.
The cosmic microwave background. It's only the most precise measurement ever made in astronomy, so I don't know.
But that's fine. I have no problem with the CMB. No problem.
Yeah. Awesome. All right. Well, I think we're reaching the end of today's episode, so it's time for us to give everyone a chance to explain where to find out more. Let's start with you, Dr. Paul Metzetter. You were just on the firing line. Where do people find out more?
Yeah, and I should point out, by the way, this holographic principle has nothing to do with the universe as a simulation.
Okay.
It's just not even talking about the same thing.
Oh, see, and LSST was going to figure out if it's a simulation, but not. No, I'm just kidding. Just kidding.
Yeah, you can follow me on Twitter and Facebook at Paul Matt Sutter on both platforms. Also, pmsutter.com. Also, my own podcast, askaspaceman.com. And you can help support all the outreach activities I'm doing by going to patreon.com/pmsutter.
Fantastic. Kimberly, where do people find out more?
People can find out more by following me on Twitter at AstroKimCartier and on my website and blog at KimberlyCartier.org.
Fantastic. And Meredith, you get the final word here. Where do people find out more about specifically you? I've started following you on Twitter. Where do people find that out?
Sure. So obviously for LSST, it's lsst.org, just in case you didn't get that. But for me, I'm on Twitter at Meredith, which is MERRDIFF. And I also have linked from there is my homepage at the University of Washington. So you can read more about my research and other cool stuff I'm up to.
Fantastic. All right, once again, I'm Fraser Cain. There's my Twitter, fcain. If you haven't already, go ahead and subscribe to this channel. Especially click the notification bell, and that way you'll get announcements that we're going to do live shows. We're going to be doing an Astronomy Cast is going to be next. We'll be starting that up, I guess, in half an hour. We're going to be talking about geoengineering, which would be super fun. How can we completely modify the Earth at a grand scale, which is going to be fun. So we'll be doing that. You're going to go over to the Astronomy Cast channel to do that. And do a bit of an experiment. On Monday, I've put in a live event, I think 3 o'clock, 5 o'clock, I forget, where I'm just going to turn on the camera and hang out with you and answer your questions and just and sort of keep it casual. So if you want to join and hang out and talk to me, that should be in the calendar for this. And if it's fun, if we enjoy it, then we'll do it again. Okay, cool. So thanks, everyone, for joining us. Big thanks, as always, to the WSH crew for running the chat, running the behind-the-scenes stuff. Really appreciate all their help. And if you want to take your fan of space and this community to the next level, go to the wshcrew.space, and you can join the community and find out how to join this chat that's down here. Super easy to do. All free. So just join up. All right, let's go to the Brady Bunch view.
I love that we call it the Brady Bunch view.
Is that, I like it. I don't know. Is that some kind of copyright infringement? I don't think so.
No.
All right. Thanks, everyone. We'll see you all next week or in like 30 minutes. All right. Bye. Stop stream.